Alright, my name's Ryan, and today we are going to be doing yet another wacky physics video. So to start us off, we're going to be doing this problem. It's you throw a ball at 20 meters per second at a 40-degree angle from the horizontal, starting at 2 meters above the ground. The ball lands on a flat 5-meter high roof. How long is the ball in the air, and how far in the x direction does it travel? Take for granted that the ball goes onto the roof and doesn't hit the wall. So below is the illustration. We have this distance d, that's the length. That's one of the things we're solving for. We have the guy here throwing the ball at a velocity of 20 meters per second at an angle of 40 degrees with a starting position of 2 meters, and the wall is 5 meters, and we're trying to find how long it takes for the ball, we're trying to find how long it takes for the ball to travel from his hand all the way to the top of this roof. And we're also trying to find the distance from where it lands up here to this character, or this person. And we're trying to find the x component there, not this distance, which wouldn't be right, or it's not what the problem's asking for. So to start us off, we're gonna keep in mind these equations. These are the kinematic equations that every person studying physics should know by heart, should be able to write these out. And yeah, so what do we know? We know we have a velocity, we have an angle, we have a y initial, and we have a y final, and we have an acceleration. What do we need? We need 4 things. We need a delta time, the time it takes for it to travel from his hand to the top of the 5-meter high roof. We need a delta x, which is the distance from that x where the ball lands, the x distance from the ball where it lands to where it was thrown. And we need the x component of the velocity, initial velocity, and the y component of the velocity, and you'll see later why we need that. So we need to decide which equations to use based on what we know and what we are trying to solve for. We're trying to solve for these two, and we have 5 things. So looking up here, we don't have a velocity final, so we can already cross out these 2 equations, which, I mean, it really just leaves us with just one equation. So we're going to be using this equation, which is position final is equal to position initial plus velocity initial times the change in time plus half of the acceleration times the change in time squared. And I've nicely set that up for you down here. Please don't be overwhelmed by the amount of writing. You'll understand it soon, hopefully. But when we're using this equation, we have to keep in mind that we have to break this up into components, right? We have to break this up into an x and y, because we can't just flat out plug in 20 and expect it to output the right answer, because we can't find how gravity is affected in this component direction, and even then it's like the thing changes, so it would be very difficult. And it's a lot easier to calculate it if we break it up into its x and y components, which is what we're going to do, and it's why we need to find the velocity initial and its x and y components. So back to where we were. Sorry for all the scrolling, it's kind of disorienting, I know, but please bear with me. So to break the initial velocity into its components, we need to do some trigonometry. And if we take a little chunk from the illustration above, we can break that initial velocity at an angle of 40 degrees, which is like 20 meters per second, into a right triangle. And we can solve for this adjacent component and this opposite component, which is labeled v initial y and v initial x, respectively. So if you don't know any trig, what I can say is SOHCAHTOA. You use SOHCAHTOA. Sine is equal to opposite over hypotenuse. Cosine is equal to adjacent over hypotenuse. You solve for adjacent, solve for opposite, and you get hypotenuse sine, hypotenuse cosine, right? So v initial x is equal to 20 times cosine 40 degrees. V initial y, 20 times sine 40. Right. Easy stuff. Then we just plug in for our y component distance equation, right? Plug in our values we know, 5 meters, 2 meters, this y component velocity, And then this acceleration, we're plugging in gravity because the ball is being pulled down by gravity in the y, but it will not be pulled or affected by gravity in the x because the x component is going to be perpendicular to the gravity. It's not going to be affected at all. So we plug in, solve for t, right? We get this equation, use the quadratic equation, and we end up getting 0.16 seconds and 2.3 seconds. Now we need to determine, since we got 2 times, we need to determine which one is extraneous, and I'll tell you why we got 2 times. If you go up here, you'll notice that this ball arc actually equals 5 meters twice. It equals it here, and it equals it here. And we need to determine, based off the numbers we got, which ones we want to use. Now, obviously, we're not going to use this one because the ball doesn't hit the wall here. It actually hits it over here at a later time. So in this specific problem, we're going to be crossing out the smaller time because it takes more time for you would intuitively you would know that this wouldn't work because the ball would land at a much later time than 0.16 seconds. Now that we know our delta time, we can solve for x. The way we solve for x is we use the same equation again, this time solving for the x component. So this time we're using v initial x and the acceleration in the x direction, which, I mean, there is no acceleration in the x direction, so that's going to be 0. Our position initial is going to be 0 because our reference point, we're starting our reference point from where the ball was thrown. And we're left with, after we cross out the non-factors and simplify it, we're left with position final, which is our distance that the ball travels, is equal to v initial x times 2.3. And our v initial x is 15.3. So S final is equal to 15.3 times 2.3, which is equal to 35.19 meters. And our final answer, or our distance, is equal to 35.2, 35.19 simplified, and our delta time is 2.3 seconds. I went really fast, and I hope you guys understood what I explained. If you did understand, please leave a like, favorite, subscribe, hit the little bell, and I will see you in the next Wacky Physics video. Thank you.